So let's look at another organic chemistry problem, sticking with the alkynes, and take a look at the problem we had put up on the boards a couple of days ago. A hydrocarbon with an unknown structure has a molar mass of 106 grams. When it's reacted with the Lindlar catalyst, the unknown hydrocarbon absorbs one equivalence of hydrogen. If we take the original material and switch it to just normal palladium on charcoal for the reduction catalyst, this time it absorbs 3 moles of hydrogen gas instead of just 1. Explain this observation and work out the chemical formula and structural formula for the compound. So let's start with our first statement with that molar mass of 106. So that 106, of course, can be divided by 14, which gives us a number of CH2 units in the molecule. Basically, there's normally about double the amount of hydrogen compared to carbon when we look at any organic formula. Sometimes it's a little bit less, sometimes a little bit more, but only slightly more, because our saturation point, of course, is CnH2n plus 2 for any hydrocarbon. But divide by 14, it goes in neatly 7 times, and we're 8 grams of mass off that target of 106 when we take 7 times 14. So we can't use that 8 grams to make more hydrogen. It would put us past our saturation limit, so we have to use the 8 grams to try and create another carbon. We don't have enough, so we have to steal 4 grams of mass, another 4 hydrogens, to make an extra carbon. So the formula for our compound should be C8H10. That's a formula that matches the molar mass of 106 grams. It's the most likely outcome. So how does that compare to a saturated hydrocarbon? Well, of course, if it was saturated, that would be 8 carbons and double the amount of hydrogen plus 2, which would give us 18. We've only got 10 in the formula, so for every 2 hydrogens lost from the saturation point, it suggests either we've formed a ring structure or we've included a pi bond. Rings and the introduction of pi bonds takes 2 orbitals and cuts down the hydrogen count by 2 each time. So maybe it's just 4 pi bonds altogether in an open chain structure, or maybe it's 2 pi bonds and 2 rings, some kind of combination like that. So we have worked out the chemical formula from the molar mass. Now, thinking about that reaction with a Lindlar catalyst, there was only 1 equivalence of hydrogen absorbed from that. And of course the Lindlar catalyst is specific to reactions with alkynes. It only opens up one of the pi bonds and it stops at the alkene, producing specifically the cis product. So only 1 mole of hydrogen gas absorbed, 1 equivalence, suggests that there's only 1 pi bond or 1 triple bond in the molecule. That explains 1 of the moles of hydrogen gas absorbed. And when we switch to just normal palladium on charcoal as a catalyst, which will absorb hydrogen to any pi bond, we absorb another 2 moles of hydrogen gas. So that pi bond, what we talked about previously, it absorbs 1 mole, then a second mole to completely absorb the pi bonds in the triple bond. But the question tells us that 3 equivalents, 3 moles of hydrogen, are absorbed altogether. So the triple bond that had been alluded to with the Lindlar catalyst only explains 2 equivalents being absorbed. So that third and last equivalence of hydrogen, when we're using just normal run-of-the-mill palladium charcoal, that suggests that somewhere else in the molecule there's also a carbon-to-carbon double bond. So we have a molecule with an alkyne triple bond, and we also have a alkene double bond in the molecule somewhere. Now, of course, we had said that our hydrogen count was down by 8 altogether, and the triple bond explains 4 hydrogens being lost from the formula. That alkene bond explains another 2 hydrogens being lost. That's only 6, and we're supposed to be down 8 from our original saturation point. So that last 2 hydrogens can only be explained if they're not absorbing hydrogen in the reduction. That last 2 hydrogens can only be explained by a ring structure in the molecule. So we have all the information we need now to propose an answer for the structural formula. Easiest one was probably an 8 carbon ring, the ring explaining 2 hydrogens being lost, the double bond explaining another 2, and that triple bond with 2 pi bonds explaining the other 4. Of course, as long as we keep to the same chemical formula, we can do a variety of molecules which would still be explaining that answer. So maybe the ring, but the double and triple bonds in relatively different positions, or maybe it's a smaller ring size, as long as we've still got the pi bond for the alkene and the 2 pi bonds for the triple bond. There's actually a variety of ones that we can look at and suggest, but it's got to come back to that formula of C8H10. The most likely answer is probably the first one, because of course the triple bond is trying to be linear at this point, and the bending of the molecule around in the ring causes stress. So an 8 carbon ring is more likely than the 7 carbon suggestion.